Excuse me. So yesterday we had a problem where we had the twin point charges, both equally spaced from the x-axis, one with the charge plus q and one with the charge minus q. And in the other scenario, we had the same charges on either side. So the question was first to calculate the electric field by magnitude and direction. So we have given a general, or not all general, but we given the formula based on using the electric field, how it is generated by a set of point charges. And we have inserted then the values for the distance vector. We assumed that we are moving along the x-axis. We had then, we were moving to C. We have actually not really given the, we have not given it for the case where exactly x is equal to h, but that you can also easily achieve by making the correction to this or making the adjustment to the respective vectors. But we have nevertheless given a plot here of how we estimate the field distribution. And also here, what you see is, I wanted to highlight again, we had here on the one hand a rough sketch of the plot with the dislike charges, and we wanted to monitor what the electric field is along this x-axis. And along this line, there's only an EX component. That is, sorry, there's only a EY component. There's only electric field component in the Y direction. This is what our formula also gave us here. And then what we plotted here, that is the magnitude of the electric field for this case. In that case, in the scenario of the dislike charges, the field along the x-axis has only a contribution from the y component. So the magnitude, this is all that enters into the magnitude, is only from the y component. And you see that matches here that the electric field is strongest at the center where x is equal 0, and then it is kind of slowly decaying. But this is the sketch here, what you have to put in as a distribution of the electric field in y direction along that x-axis, only a y component. And here, on the other hand, this was a second case with the like charges. You have a contribution to this magnitude only from the x component, because in the second scenario along the x-axis is only a x component of the field. So, and then we were getting to the part C of the problem, is to calculate the voltage between the origin and an arbitrary point P, which is also located on the x-axis. So that means we want to have the voltage V. So you can use V or you can use U as you like. It is both common notation. In general, it is good to stick to the common notation, so not use completely random name for any of these quantities. So point 1, that is actually the origin 0, 0, 0, and P2. So you remember how to get the voltage. What do we have to solve? We want to, that is the integral, and of course this integrand is over some certain path, some curve. It's our curve T. So remember, we have here our setup where this is x, this is y. We have our charge q1 at the location h and q2 at the location minus h. And this here in the, oh, sorry, was meant to went to the origin. This is P1, and there's some other point P2, and this is our line we integrate along. So that's already very agreeable that this is along the x direction. That indicates that it will be nice for us with respect to parameterization of the line of the curve. So anyway, we nevertheless take this into consideration, parameterization. We have calculated V12 is the electric field, and we use a parameterization of the electric field and the parameterization of the path. And the line element will be coming then the derivative here of the general path with respect to the line parameter that we define. And the parameterization now is we make r a function of lambda. This is a lambda, small lambda. That means r, vector r at lambda 0, that shall be our r1. So that is the origin of the coordinate system, that's 0, 0, 0, is plotted here. And on the other hand, we have r for lambda equal to x, that is r2, x 0, 0. So, and why is that? Because, yeah, that is the parameterization of our line that we chose. We make an r of lambda, that is lambda 0, 0, is lambda ex. So you see this is something you can do by inspection that is very thankful that this is just in alignment with the axis, the coordinate axis. So what is the tangent vector? Well, the tangent vector is the tangent to the line element based on the parameterization parameter, that is d r by d lambda. And what is this? We have r specified by the parameter lambda. So you just look into this equation here. You take the derivative. So it is, we insert that here. We have only an x component, and we take the derivative. So it is just 1 times ex. So you see this seems maybe a bit overhead for, given that this parameterization, yeah, I mean, you can see this really by inspection, but if you work through that in the formal way, then you can also apply it when you cannot do it by inspection anymore so well. So then the V12 is obtained by integrating from lambda 1 to lambda 2, integrating the E field, because what we have made use of is that our line parameter er is ex d lambda, right? That follows right here from that forming of the tangent. So this is a general form. Then we inserted here the dr by d lambda is 1 times ex, and at the ex being the unit vector, and the field itself. So we can go now into looking at the separate cases. Case A is where we have the dislike charges. Sorry. The field on the x-axis was q over 4 pi epsilon naught over, sorry, that is. And for the case B in one setup, that's the case when we have the like charges. Then we have the formula for the electric field, 1 q q over 4 pi epsilon naught lambda square plus h square 3/2 2 times lambda 0, 0, only a x component. Let's get back to case A. Insert this electric field into the equation here. So we want to, for the scenario where we have case A, is obtained by integrating as above here from 0 to x. Insert this for the electric field, q over 4 pi epsilon naught lambda square plus h square to the power of 3/2. And we see we have only a y component here, which is minus 2h, enters also the factor times Ey. This is from the electric field. And then you see here from the line element, we integrating along this line element, we get the Ex, we're integrating that over lambda. And now you see the electric field and the orientation of the line element have no common, there's no common component to it. We have only y component for the electric field, but the line element is only in Ex. That means this inner product here is 0, and as a result, the integral is very easy to resolve. There's just 0 voltage as we move along. And that makes sense if you look at what we had said. If you move along an equipotential line, then there is no there's no variation on the voltage. You are on equal potential. The voltage is the potential difference between 2 points. So if at both points the potential is equal, so that is exactly what we have. We have here some isoline or an isosurface for the 3D case, and as long as we move there, the voltage difference between any of those points on this line or for the 3D case on this surface is basically 0. It's vanishing. And in the second case, it might look different. We hope so. Otherwise, it would be a bit boring. That would be also, we can already see that. I mean, we saw that in the second case, if we move along, well, let's see. Let's see what it yields. So now let's look at case B. Same procedure. We use the electric field this time from here. Insert that into the integral. It runs from 0 to x. Is q over 4 pi epsilon naught lambda square plus h square, everything to the power of 3/2. Then here we only have the x component. So this is times 2 lambda times Ex. Then comes the line element, Ex, the lambda. And there you see right away, this time it is not vanishing. This is 1. So that means we can keep going on and integrate here from 0 to x to q over 4 pi epsilon naught. And here we have lambda over lambda square plus h square. And that we have to integrate now. Okay. What could we do? Doesn't look, not, I wouldn't say terrible, but it also doesn't look perfectly neat. But we actually find an easy way for that. We can do here a substitution and make use of u, which is lambda square plus h square. And that we insert here. If we do that, then we have to also accommodate our line element that the delta, the lambda here. And how do we find what we have to do that? We take the derivative of this substitution term u with respect to lambda. So you just take derivative here of u with lambda, you see lambda squared derived gives you 2 lambda. This here has no lambda component, that is just vanishing. But then you see that the d lambda becomes du by 2 lambda. So let's insert that and see whether that becomes any nicer. We have, let's pull the things that are not dependent on the integration variable we can pull out. So we have here 2 over 4, that's a half. The q is also not dependent, there's a half here. We have the pi epsilon naught. And then our integration, we have now adjusting, we have done a substitution, we have the lambda is 0, so we run now from u of lambda equal to 0 to u of lambda equal to x. We still have our lambda here, but we have substituted what is in the denominator, that h, the lambda square plus h square by the u. The exponent here, 3.5, remains. And the lambda is now, after the substitution, the u divided by 2 lambda here. So that actually is quite neat because you see this here cancels out. And what remains is q over the 2 that we have here at the end. We pull it also to the front, so it's 4 q over 4 pi epsilon naught. And the integration runs from u equal u of 0 to u of x. And this here is u to the power of minus 3/2. So let's integrate that. That is very easy now. This is minus 2 times u to the power of minus 1/2. And here we run from h square to x square plus h square. Sanity check. This is what we have integrated. What if we take the derivative with respect to u already of, so this is not part here of that equation, but it's just a check here. We insert what we have integrated here, our integration result, and take the derivative with respect to u. So we have here a power of minus 1/2. That means that goes in as a factor in front. Minus 2 times minus 1/2 is just plus 1. And what happens to the exponent? That is reduced by 1. So instead of u to the power of minus 1/2, we have u to the power of minus 3/2. And yeah, that is exactly the value that we had here. So we have obviously done our integration right. How about the integration boundaries? U of 0. Well, you know, the u setting lambda here to 0. What remains is h square. So yeah, lambda is just the integration parameter, the line parameter, actually, the line parameter that we have picked. We could have also picked s or, yeah. So it is not any physical quantity, it's just a mathematical substitute. And you put lambda equal to x, then you get x square plus h square. So I mean, that is a little bit of a know-how, a little trick, what you have to do in with this substitution to make the integration actually quite easy. So otherwise, yeah, you can consult your mathematical handbooks, and it also gives you sometimes suggestion on how to proceed. But this is also a bit a matter of your experience, how frequently you have done such problems. So it is well to train on various examples. So then we have here q over 4 pi epsilon naught, and now you set in there the integration boundaries. So it runs from I mean, the endpoint, it is x squared plus h squared. So we have here this 2. Let me already pull that out. We have here 2 over 4. So I pull that 2 to the front. So then I will insert that remaining here. 1 over x squared plus h squared square root plus 1 over, well, square root of h squared is 1 over h. So that here would be our final result. So you see we have computed now for an arbitrary point x on the x-axis our voltage for the second scenario, and that is the voltage between the origin and that point. In the first scenario, we figured out there is nothing happening because we are moving on the equipotential line. And then we have also problem D remaining that asks us what work is necessary to move a test charge from infinity to the origin. Calculate the work to move Q from infinity to 0.1. So we want to have the work infinity to 0. Did it ask for an arbitrary point? No. Yeah, to the origin. Well, can make use of the voltage that we have computed, because the work is the charge times voltage. Now we just have to select the right point because we have given the voltage. So we know the voltage is here an arbitrary point on the x-axis at the point 2, and 1 is the origin. For case A, we have the case that as we move here from the origin point to any point x, so that x could be now would be in infinity. So path of integration along the equipotential line is along the equipotential line. And for that reason, our voltage here is 0. And accordingly, our energy is also 0 here. And how does it look for equal charges? Yeah, for equal charges, you see that you can insert here x going to infinity. Just checking, cross-checking here. Case B, we have also the work done by Q times, we have to take the voltage from 0 to infinity, and that means we let x, we take the limes, so the boundary value when x goes towards infinity, and what have we obtained for the voltage? So we keep the Q, and the voltage here, that is the formula we have just above here, right? This one here. We let that go to infinity. The x, then that is Q over 2 pi over epsilon naught, and that is minus x squared plus h squared. You just insert that and take the boundary value for x going to infinity. So what happens when that goes to infinity? The whole expression here in the bracket is vanishing because your denominator becomes increasingly large, and the whole term here goes to 0. So what remains is only the second term in the bracket, and that means here in front you have Q times Q, 2 pi over epsilon naught times 1 over h, and that would be also here your final result, and this would be also here final result. So yes, then we have computed the work that we need to perform to bring a charge into the origin here from infinity. So in the case with the dislike charges, it actually doesn't take any work. And in the case with the like charges, yeah, we get some contribution. Do you have questions? So by the way, this was second problem of the tutorial notes. I mean the tutorial problem notes, and you can find further problems, and I encourage you also to look at those, and not all of them, but quite a few we will deal with here, and then you can already practice and see if you can, uh, yeah, can can put in some thought if you already know how to go about it. So, so let's look at this question. Um, what is a, so to say, fundamental law of electrostatics? One could say that that fundamental law is that actually electrostatic fields are conservative, and I want to give you some um, example what that means. And also in view, we had earlier today, we had this question with, or we had the a specified force field where we were computing the potential from, and once we had the potential, we could also use that to get the electric field again. So if you have an arbitrary field there, you might want to check also whether this is a viable electrostatic field, whether it satisfied the need of being a conservative field, and that what we are doing now will also give you some insight on that. So the electrostatic fields are conservative, meaning they are preserving energy, P1 to P2. We can integrate the electric field along some curve. And we have said key is that this integration is independent of path. So let's assume you have here two planes at different potentials, phi 1 and phi 2. So obviously you will have some field lines running from one potential to the other potential, because these two potentials are not the same. And then now you have here a point 1, and somewhere else you have a point 2. And if you choose an integration path like that, or if you go like this, doesn't matter. That also implies then if you return to the original point and you make a circular integral, then that is vanishing. So that would be the scenario where you just go from here and then here. That is vanishing. So the electric field is a gradient field. That means the electric field is obtained here by negative of the gradient of phi. The negative is just a convention, and that phi is a scalar field. That means the rotor or rotation of E is 0. This is the same as the curl. This is just a different name. If you see that, uh, no difference at all. But be prepared, because some books use uh, the rotation, some use curl, some use, or you can use the Nabla operator. This is all the same. And the rotation or the curl of the gradient of the scalar potential is vanishing. That means you have no vortices here in your field. And you can actually verify that. Take an arbitrary uh, scalar field, take the gradient, take the rotation, you will see it is vanishing. It's very easy to show. Just have to write it all out. The rotation or curl in in Cartesian coordinates, that I'm sure you know how to write that by heart. This is simply then 0. So the assumption is now that we are in Cartesian coordinates. So that means you have an Ex, Ey, Ez. But the curl is vanishing in all situations. Just this here, writing it out as such, only applies in Cartesian coordinate system. Keep that in mind. So if you look at the individual components here, it becomes apparent that this fact that the curl is vanishing, and because each of these components vanishing, you can write that in this more general form that uh, you know, this applies, and I and j can be 1, 2, or 3. And you know what x1 is then? X sub 1, x sub 2, x sub 3, that would be x, y, and z, right? Just x1 is x, x2 is y, x3 is z. Yeah, sorry. Sorry? What did I do? Is it okay? If you, this is a general case for the 3D. If you are in 2D, then it's just as well applicable. Of course, then you only have 2 components. And if you, as we most of the time, but not always, you're free to choose whether you use X and Z or Y and Z, but assume you use X and Y, then if that applies, then you're fine. Again, in Cartesian coordinates. I have to stress this. Maybe, probably tomorrow we will have another recap on math. Then you will also see, maybe appreciate more that this makes a difference. So if we have a field which is described, the x component of the field is given by 2x, the y component is given by y. Our question is this conservative? Let's check. So we take the x component, derive it with respect to y. The x component is 2x. And we take the y component and derive it with respect to x, question mark. So what do we obtain here? This is 0. This is 0. Yes, it is working. Conservative. Okay. So this is a bit to do checking whether something is conservative. And you can do that, for example, on the problem we had today. And we have now also a further question coming up. And that is our problem 4 from the set of tutorial questions. Yeah, let's look at this one here. The following two-dimensional force field is given in Cartesian coordinate systems. In the Cartesian coordinates. So the force field is a function of x and y. It is given by a constant c times, and then you have here 2x times y, that is the x component, and the y component is x squared. C is constant. Is this force field conservative? Well, just plug it in. This is our force field, x and y. We can write that alternatively as 2xy x squared. So is the x component of the force field derived, partially derivative of the x component of the force field equal to the partial derivative of the y component of the force field with respect to x? Let's check that out. So this is the question. So x component is 2cxy, and the y component is cx squared. Let's take the derivative. This is 2cx, and this is 2cx. Oh yeah, that is nice. So yes, we have f is conservative. It would be otherwise also quite a pity, because then it wouldn't be nice to proceed with this problem if that wasn't now given. So B, calculate the work which is performed during the motion along the sketched path. So what is this? You see here, this is a coordinate system. I mean, the force field is not plotted, but the path is plotted that we want to integrate it over. That starts here at the origin of the coordinate system here. We start at that section that is called 1, and this is described by the curve where y is equal to x squared. We go here till we have x equal 1. Then we move down with with constant x down in negative y direction. This is the second stretch. This is our section 2. And then we move from 1 to the origin. I guess in some way we can already assume what should be coming out, but let's try it whether it is really holding true. We want to convince ourselves of that, but we have stated that this is a conservative field. So, I mean, we have not stated, we have shown it in example A by showing that this integrability condition, or that this is satisfied. Work given by integration force over the path. And now you remember we have some line here, we have some force field here. So we have the line segments. Oh, yeah. And these green arrows, these are basically the tangents to the line. Recall tangent to the line, which we have parameterized, in this case again is lambda. That is given by the derivative of lambda with respect to lambda. Then we go about our first line segment, right? This is this is this one here, where y is equal to x squared. So we denote this work that has to be put in, or which is being extracted or put in, and depending on what the result will be here. This is W1. And accordingly, for the second stretch, it will be W2 and W3 for the third stretch. We add them all together, then that will be the work for our closed loop. So here we integrate from lambda 0 to lambda 1. So we want to parameterize by lambda. And now how does this parameterization look like? So we know the y is equal to x squared. And we parameterize it by saying x equal here to lambda. Then our R1, that's basically R1 of lambda. This is our first part. We have to, because we have these 3 stretches, we have to go through this procedure 3 times. So this is now for our first element. So the running vector along that path in that first element is here R1 as a function of lambda. And now you see, because y is equal to x squared, and we say x is equal to lambda, that means we have that as a function of lambda, and y is lambda squared, right? And this is running from 0 to 1, that lambda, because your y is x squared and x is equal to lambda. So this, what we have done, we have now, you know, earlier we have here this, we follow this line here, and we have here a function of y and x, y is equal to x squared. We would like to have here a single parameter that we integrate here. So we want to parameterize it. So by doing so, when we say we introduce this lambda here, then you have here for that integration path now only, yeah, basically you have a single parameter here. You don't have to think about how to accommodate. I mean, you have a curve and it depends only on a single parameter. So that makes it easy to integrate. Otherwise, it would be difficult to go about it. It's a line integral, and somehow you have to make it a function of one parameter so that you can perform the line integral in a nice way. So you say this is x, so you can put it in here as the substitute, or you have reparameterized here, so you have this a path vector that describes how the path is proceeding, and this is only dependent on a single parameter. So now you can easily integrate. So that is the advantage of this parameterization, that the integration becomes feasible and easy also. I mean, if you were to do some numerical integration, then you can always do that. But if you want to have an analytic solution, then you have to find some so to say, workarounds. And this parameterization allows you to do that. So we have the integration here over, and we introduce here the parameterization of the line, and according to that also the parameterization of the force field. And we bring in here the adjusted line element. This is not just dr anymore, but it is dr of lambda derived with respect to lambda, and then here comes the lambda again. So you see we have essentially nothing altered, but we have it adjusted to the new parameterization. So lambda, as you see here, it runs from 0 to 1. So then lambda 0 is 0 and lambda 1 is 1. The electric field, as given here, is c 2 times xy, and here x squared for the y parameter. But the x has been turned into lambda, and the y has been turned into a lambda square. So that gives us 2 times lambda to the power of 3. And the y, as we just said, lambda square. Yeah? This becomes the new parameterized version of our force field. And for the line segment, you take here this parameterized version of the path, and you get here the tangent by taking the derivative of this here with respect to lambda. And lambda derived by lambda is just 1, right? And lambda square gives you here 2 lambda. And now we see we can pull out. We integrate from 0 to 1. Now you take here this inner product, yeah? You take 2 times lambda to the power of 3 times 1. And you take here 2, sorry, not 2. You take here, for that lower component here, this is lambda squared times 2 times lambda. So this is also 2 times lambda to the power of 3. You integrate here over lambda. So let me add here some note for this force field, this parameterized one, just as a reminder. That is now the constant times 2 times the x is the lambda, the y is the lambda square, yeah? So that's how the lambda 3 comes about. And the y is already the lambda square. So this is your parameterized force field. So just compare it with the original version. That was c times 2xy. And here x squared. This is, and here the derivative of r of lambda, the parameterized curve. There you take this here. This will give you the tangent element, and this is 1, oh, and here 2 pi, 2 lambda. So you see, you have taken this one, inserted here, or here, let's say here, and you have taken this one here. So this is what you get. So then this seems to get quite easy now. We add these two together. This is just 4 times lambda to the power of 3, integrating variables lambda. Then let's do this integration. The integration of lambda to the power of 3, by the factor 4 we keep here, that is 1/4 times lambda to the power of 4. And the starting point is 0, the end point is 1. Insert that, you get c times, yeah, 1 to the power of 4, which is still 1, times c minus c times 0 to the power of 4. So c is your final result. Now let's move along the second stretch of that closed loop integral. That is number 2. And you see, you look up here in this plot, we move from the point 1, 1, x is 1, y is 1, to the point 1, 0, x is 1 and epsilon or y is 0. So we introduce a new parameterization for that stretch. So we have a new lambda now. I'll use the lambda again, but it's a different lambda now. It is for the second stretch. So we move from point 1, 1 to the point 1, 0. Lambda shall also again run from 0 to 1. But you see the parameterization is very easy now. This is R2, because the 2 signifies that we are on the second stretch of that closed loop integral. And that means we have a constant x, which is 1, and the y is varying with lambda. So we start at 1, 1 and go down to 1, 0. So we subtract here lambda. So if we start with lambda 0, then this is here 1, 1. And if we reach lambda 1, then this here becomes 1, 0. So the parameterized force field is c times now 2. That is the 2 that we had the original factor. Then our x becomes 1, and our y becomes 1 minus lambda. And here our x squared becomes 1 squared. So what about the derivative of, that should be actually the derivative of r2 is lambda. Just take that from above here, take the derivative. 1 derived to lambda by lambda is 0. And then the other 1 minus lambda is minus 1. Insert that now into our second stretch of the work integral. Parameters running from 0 to 1. C times, that is our parameterized force field, 2 times 1 minus lambda, 1. That is our tangent, our adjusted line element. That is c times the integral from 0 to 1. Now take the inner product. This here times 0 is 0. And this here times minus 1 is plus minus 1 here. And that is c times, if we integrate that, it is minus lambda integration boundary is from 0 to 1, that is minus c. This is the result of the second stretch. Now we have to take the third stretch, and there you see again the third one was moving from x equal to 1 and y 0 to the origin back. So we move from 1 0 to 0 0. Now our third r, signifying the 3, again the third path segment of that closed path, that we can write as 1 minus lambda in 0, with lambda running from 0 to 1. Then the derivative of r with respect to lambda, you see immediately here minus lambda, that is giving a contribution which is minus 1, and down there is no contribution. Then take the force field, the parametrized one, that is c times here the x becomes, oh, should not be green, is 1 minus lambda. The y is 0, and here we have x 1 minus lambda, and everything here squared. That is our parametrized force field. So insert that for the third segment, parameter running again from 0 to 1, c times force field. The x component here is times 0, so it's overall 0. We have here 1 minus lambda squared. And then we take it with the inner product here of the tangent of the line element, that is minus 1, 0, integrating over lambda. So c times, so 0 times minus 1, we can, yeah, you see actually this one times this one is 0, this one is times this one is also 0. Let me write that also in a different ways to maybe appreciate it also in a different, from a different perspective. I can write the force field also now here is 1 minus lambda squared, and it has only an EY component, and the tangent vector is minus 1 times the EX component. So you see you get EX and EY here, this is 0. Could have seen that also right away from the line above. So this gives you no contribution. And yeah, then you have your total energy, or the total work is W1 plus W2